Hello, a very good morning to all. I hope you all doing well. So, what's our today's session? We are going to study today hydrocarbon, right? So today is our very this hydrocarbon chapter carry very good weightage of question. So try to understand this chapter and I'm going to explain each and every topic because it is a crash course. But even I'm going to explain each and every topic related to this hydrocarbon. We are going to study hydrocarbon now in three parts. That is alkane, alkene, alkyne, and one another that is a aromatic benzene. Okay, that is aromatic compounds. So it will going to be very interesting session for the today class. So let's start with the today session. Is I'm audible to everybody? Yeah. Okay. And beta, if you have any doubt related to any questions or any topic, please ask in chat box. Okay. I'm going to reply each and every questions related to your doubts and even any small or big, any kind of doubt you can ask. Okay. So let's start with the today's session. That is hydrocarbon, right? Okay. So first of all, as we already discussed, we're going to study hydrocarbon in three parts, that is alkane, alkene, alkyne, and aromatic benzene, right? So first of all, let's read some important point regarding alkanes. Okay. So first of all, how can you prepare alkanes, right? So I'm not going to explain each and every topic. I'm going to explain only those topics which are very important and questions were coming in a previous year. That is the PYQ questions basically coming from these topic only. Okay. So I'm going to explain these topics in a very detailed or in a very easy way, right? So let's start. Now, first of all, how will you prepare alkane? Okay, if someone asks how will you prepare alkane, the first point is alkenes on hydrogenation, right? That is the first method. That is alkenes on hydrogenation. What is hydrogenation? Hydrogenation means reaction with the hydrogen in presence of some suitable catalyst. So alkenes on hydrogenation in presence of nickel, platinum, or palladium give alkanes. And this reaction is also called Sapner or Sandron method. Here, this is alkene, R CH double bond CHR, and this is hydrogen. And we when we treat this with nickel, platinum, or platinum, then alkane formation takes place, right? Second point is from alkyl halide. How will you prepare alkane from alkyl halide? Alkyl halide, all alkyl halide except fluoride. Okay, so all alkyl halide except fluoride on reduction with zinc and dilute hydrochloric acid give alkane. For example, if I'm treating alkyl halide with H2, for example, I'm treating CH3 and Cl in presence of what? In presence of dilute hydrochloric acid and zinc. That is zinc and dilute hydrochloric acid. That is H plus. So what we get, beta? We get CH4, right? We get CH4. But one point remember here, fluoride cannot be, by using fluoride, we cannot prepare alkane in this method, right? So fluoride is the exception. Next method is alkyl halide upon treatment with the sodium metal in dry ether give alkanes and also called Wurtz reaction. So this is a very famous reaction. Three types of reaction now: Wurtz reaction, Wurtz fatigue reaction, and the fatigue reaction. In Wurtz reaction, two different alkyl halide are taken, and the product we obtained is if we take ethyl chloride, then we get butane. If you take propane chloride, then we get hexane, and so on. We get twice as the reactant, right? If I'm talking about Wurtz fitting reaction, in a Wurtz fitting reaction, there is a, yeah, when we treat chlorobenzene in presence of 2Na plus ClCH3, then what happened, beta? In presence of dry ether, 2NaCl removed, and the formation of toluene takes place, right? And the formation of toluene takes place. So this is known as Wurtz fitting reaction. We are going to study this in aromatic compounds, right? So this is the Wurtz fitting reaction. Now, so next is one more important thing. It should be noted here. Wurtz reaction is preferred only for the preparation of symmetrical alkane, right? If we prepare asymmetrical alkane, if we take asymmetrical alkyl halide, then we get the mixture of product. Okay. If we let us understood with example, that is, if I'm taking CH3Cl and CH3CH2Cl plus 2Na. What we'll get? We'll get the mixture of product. Either we get one CH3, one CH3 combined together to form ethane, or two CH3 combined together to form butane. So it is a mixture of product is possible. Okay, that's why Woods reaction is prefer only for the preparation of symmetrical alkane, not asymmetrical alkane. It should be noted here, right? Okay. The next question is removal of CO2 from the carboxylic acid in presence of a soda lime is called decarboxylation. Always remember this. What is decarboxylation process, beta? Removal of CO2. As the name suggests, now decarboxylation means removal of CO2 from the carboxylic acid in presence of soda lime is called decarboxylation. Now, what is the sodium salt of carboxylic acid? Point to be noted. Sodium salt of carboxylic acid. What is this? Sodium salt of carboxylic acid? This one, right? Sodium salt of carboxylic acid give alkanes on decarboxylation in the presence of soda lime. In presence of soda lime. What is soda lime, beta? That is a mixture of NaOH plus CaO. This mixture is known as soda lime. This point is very important. The mixture of NaOH plus CaO is known as soda lime, and sodium salt of carboxylic acid. When we treat sodium salt of carboxylic acid, that is a CH3 COONA. This is the sodium salt of carboxylic acid. So when we treat sodium salt of carboxylic acid with the soda lime, that is NaOH plus CaO, we get CH4, right? That is alkane. I hope I'm clear. Okay, everyone. Okay. If you haven't doubt, beta, please feel free to ask. Okay, right. Okay. Let's proceed with the next point. Right. Now, this is very important point regarding the physical property. Some questions were coming in a previous examination related to this point only, and this is very easy to remember, right? Okay, the first point is the boiling point of alkanes increase with increase in the molecular weight due to increase in the van der Waals forces. One point noted here, boiling, if I'm talking about boiling point, first of all, boiling point depends on the number of carbon content. Okay, as the number of carbon content increase, for example, if I'm talking about this is here only two carbon is there, here three carbon is there, here four carbon is there. So as the number of carbon content increase, boiling point increase due to increase in the van der Waals forces. So this is the first almost basic point, right? So if I'm talking about N-pentane and hexane and heptane, obvious N-heptane has a more number of carbon atom, so their boiling point is more. Next, as the branching in alkanes increase, as we increase the branching, boiling point start decreasing. If I'm talking about the primary hydrocarbon, or we say primary cation, secondary, tertiary. Okay, then I'm talking about the tertiary having more branching as compared to primary carbocation. Okay, or if I'm talking about anything, primary alcohol, secondary alcohol, or tertiary alcohol, right? So as the branching increase, boiling point start decreasing. Why? Due to decrease in the surface area. One important point. Here example also, N-pentane, isopentane, neopentane. We know the neopentane is the tertiary, isopentane is secondary, and N-pentane is primary. So out of these three, which one having highest boiling point? That is N-pentane. Why? Because it is primary and there is no branching in N-pentane. Right. Okay. The next and most important thing is what about the melting point? So alkane, or we say a hydrocarbon, so basically alternation effect. What is this alternation effect? Alternation effect means, beta, even number of carbon atom have a higher boiling point. Point to be remember, that is even number, right? Even number of carbon atom has a higher boiling point than the adjacent alkane of the odd number. If I'm talking about CH3, CH2, Cl, and CH3 and Cl. Okay. So if you consider a long chain like CH3, yeah, CH3, CH2, Cl, and this is CH3, CH2, Cl. So out of these, here three carbon is there, and the below one there is only two carbon. So even number of carbon atoms show higher boiling point as compared to odd number, because in the this one only three carbon is present now. So and this is valid only for the adjacent alkane only. If we given 7 carbon and four, or we say 4 carbon, then out of this 7 carbon, 4 carbon, which will have a higher melting point. Don't say blindly that key 7 carbon will be more boiling point or 5. जस्ट पॉइंट टू बी रिमेम्बर हियर ओनली एडजेसेंट एल्केन. एडजेसेंट एल्केन मींस क्या, समझे इस चीज को, कि मतलब ऐसा नहीं है बिल्कुल भी कि तुम ये सोचो कि अगर मेरे को किसी ने बोला कि 7 ऑड नंबर है और 4 तो इवन नंबर है तो 4 का ज्यादा हो जाएगा, नहीं. बस 7 को 6 से कंपेयर कर सकते हो. आउट ऑफ 6 एंड 7 ओनली 6 विल बी ग्रेटर. बट इफ यू कंपेयरिंग 7 विथ 4, देन ऑब्वियस 7 विल बी मोर मेल्टिंग पॉइंट एज कंपेयर टू 4. ऑड नंबर इवन नंबर पॉइंट कहाँ ध्यान रखना है, बस एडजेसेंट के लिए, ना कि पूरे के लिए. ठीक है, चलो. नाउ alkanes give alkyl halide on a photochemical halogenation. This is very much clear कि whenever we take a hydrocarbon, that is alkane, and on in presence of sunlight reaction with the Cl2, it will give CH3Cl, that is alkyl halide. In this also there's some important point to be noted, that is with chlorination is possible. Fluorination is not possible because the reaction is very explosive. Iodination is reversible in nature. Okay. Okay, and bromination is also possible. So chlorination and bromination is possible. There is no problem in this, but fluorination is not possible because the reaction is very explosive, and iodination is not possible because reaction is reversible due to formation of HI, right? Okay. Now, next move to the next point. That is a straight chain alkane converted into branch chain alkane in presence of anhydrous aluminum chloride AlCl3 and HCl gas is called isomerization. So what is isomerization? When the straight chain alkane converted into branch chain, which reagent we use? That is AlCl3 and HCl gas, right? The next is N-hexane give 2-methyl pentane and 3-methyl pentane in the presence of anhydride AlCl3 and HCl. So point to remember this, N-hexane give 2-methyl pentane and 3-methyl pentane in presence of AlCl3 and HCl. And conversion of N-alkanes into aromatic hydrocarbon in presence of Al2O3, Cr2O3, MO2O3 is called aromatization. So this is also very important. Whenever you have to convert alkanes into the aromatic, what reagent we use, beta? Al2O3 or Cr2O3 or MO2O3. So these are the reagents basically used for the conversion of an alkane into aromatic hydrocarbon, right? Okay. Next, move to the next question. That is minimum 6 carbon required for aromatization. Okay. Or N-hexane converted into benzene in the presence of this. So this is a very important point you must be remembered. If I'm talking about aromatization, means conversion of N-alkane into aromatic compound. And for this, we need 2 criteria. One, minimum number of carbon atom must be 6. And what reagent we use, that is a Cr2O3, Al2O3 or MO2O3. So these are the reagent used for the conversion of N-alkanes into indirectly into aromatic compound, that is benzene, right? So this point must be noted. Okay. Shall I proceed to the next slide? Yeah. No doubt? Okay. Now, so this is all about the alkanes. Now we are going to discuss some points related to alkenes. Okay. Now, the first one is how we'll prepare alkenes. Just like alkanes. Okay. So alcohol give alkenes on the dehydration in the presence of concentrated H2SO4 at 170 degrees Celsius, or many times it will be written as 443 Kelvin. Okay. Many times it will also written as 443 Kelvin. So alcohol give alkenes on dehydration, like that when alcohol is treated with concentrated H2SO4, OH and H, removal of H takes place and the formation of RCHCH2, that is alkene. So this is the first method. Second method, and it is also a most important method, that is in presence of S3PO4, right? S3PO4 or P2O5 at 200 degrees Celsius. Alcohol give alkene also. So this is also preparation of alkenes from alcohol itself, but here the reagent is different, S3PO4, and the temperature is slightly more than H2SO4, right? The next is in presence of Al2O3, same reaction proceed, but the temperature is 350 degrees Celsius. Understood? 350 degrees Celsius. That is, whenever there's a total, how many method from alcohol for the preparation of alkene? Three method. One with the concentrated H2SO4 at 170 or 443 Kelvin. Another is with S3PO4 or P2O5 at 200 degrees Celsius. And the next is with Al2O3 at the 350 degrees Celsius. And in all these three methods, we prepare alkene from alcohol. Okay. Okay. Next, move to the next question. That is order of dehydration of alcohol. What is the order of dehydration of alcohol? If I'm considering here is a tertiary alcohol, secondary alcohol, and primary alcohol. How will you draw beta? Tertiary alcohol. Yeah. That is CH3, COH, CH3, CH3. So this is the tertiary alcohol, right? And how will you draw secondary alcohol? That is CH3, CH, OH, CH3. So this is secondary alcohol, right? And what is the primary alcohol beta? CH3, CH2, CH3, and OH. So this is primary alcohol. So if I'm comparing primary, secondary, and tertiary, what is the rate of dehydration? Then the rate of dehydration will be tertiary. Why tertiary? Because tertiary carbocation is much more stable. Okay, tertiary carbocation is much more stable as compared to secondary and primary. Therefore, this or the dehydration reaction follow what? Carbocation mechanism. Okay, formation of carbocation takes place. So we know that out of primary, secondary, and tertiary carbocation is much more stable. That's why order of dehydration of alcohol is tertiary, secondary, and primary alcohol. Right? Okay. The next important point is the removal of hydrogen halide from the alkyl halide by alcoholic KOH or NaNH2 is called dehydrohallucination. And there is one important rule is also there, that is the Sirjeff rule, to find the major or a minor product. So how this reaction look like? For example, if I am taking CH3, CH, Cl, CH2, and CH3, and we react this with KOH alcoholic. Then what happened, beta? One KCl is removed. Okay, KCl is removed. Now OH and one H is also eliminated. So which place? That is, this is a group. This is a alpha carbon. So this is a beta carbon. This is also beta carbon. So two product for me, possibility of two product is there. Either H is removed from this beta or from this beta. If we remove from the first end one, that is CH2 double bond CH, CH2 and CH3, right? Right? Okay. So this will happen. Now, one another option, like if we remove H, right, from this beta, that is CH and CH3. So out of these two, one product is in major and one is in minor. So which one is major and which one is minor? This will explain by the Sirjeff rule, right? This will explain by Sirjeff rule. So according to this rule, if I'm considering this one, है ना? So इसके पास ध्यान से देखो, यहाँ पे क्या है? ये दो donor group है, so it behave like a secondary, like it having two donor group, but here only one alkyl group is present. So major product कौन बनेगा? नीचे वाला. According to Sirjeff rule, the major product is formed by those which having the equal number of hydrogen on the either side of the double. So this will be the major product, right? So this is known as dehydrohallucination. Point to remember, dehydrohallucination. Here the removal of a halogen as well as water. Both removal of takes place. That's why they are known as dehydrohallucination. Is it clear to everyone? Yeah. If you have any doubt, beta, please feel free to ask. No? Okay. Now, next point. Order of dehydrohallucination of alkyl halide. Alkyl halide. What will be the order that is? We already discussed now. For dehydration of alcohol. That is tertiary, secondary, and primary. Here also carbocation comes into the picture. So the order will same. That is tertiary, secondary, primary alkyl halide. Now, the next point is removal of H2 from the substance in a presence of a zinc dust or a methanol or zinc copper couple in alcoholic solution is called dehalogenation. Point to remember. Okay, in presence of zinc dust or methanol. Now, on dehalogenation of alkyl halide, give alkenes in the preparation presence of zinc dust. For example, if I'm taking gem halide means what? Halogen atom are two halogen atom on the same carbon atom. This is called gem halide. When we treat gem halide with the zinc dust, what will we form? That is alkene plus ZnX2. Similar, when we treat 1,2-dihaloalkane in presence of a zinc dust, always a vicinal dihalide because two halogen atom on the two adjacent carbon atom. They are called the vicinal dihalide. Then we get what? Then we get alkene plus ZnX2. Similar, hydrogenation of alkynes in presence of Lindlar catalyst, that is PDCl4 BSF4. Point to be remember, this is very, very important point, beta. What is Lindlar catalyst? Lindlar catalyst is PDCl BSO4 in presence of quinolone gives alkenes. So whenever a hydrogenation, whenever we prepare alkene from alkyne through hydrogenation in presence of Lindlar catalyst, that is PDCl4 BSF4 or quinolone, give alkenes, right? Internal alkynes give cis alkene on reduction with Lindlar catalyst. Okay, so point to remember, this is beta. Internal alkyne give cis alkene on reduction with the Lindlar catalyst, right? Now, the reduction with the sodium and ammonium, internal alkyne give trans alkene. So this point is very important. When we reduction of alkyne, okay, with Lindlar catalyst, yani whenever we take Lindlar catalyst, then cis alkene is formed. But when we take sodium and ammonia, then trans alkene is formed. Okay, so this point is very, very important, and try to remember this point because many time question asked from the Lindlar catalyst or a sodium ammonia, and what happened in which case cis alkene form, which case trans alkene is formed. So these are the very, very important point. Try to remember them, right? Okay. Now, this is also a very important thing, that is the ozone lysis of alkene. And I'm going to explain one. I am going to share a one trick with you that you will easily solve questions related to ozone lysis of alkene, right? So what is ozone lysis of alkene, beta? Basically, when the alkene is treated with ozone in presence of zinc and H2O, then the formation of either aldehyde takes place, aldehyde ketone takes place. So we are going to discuss in which case which is formed and which is not formed. Okay. So just follow one simple trick here. That is, for example, if I have but2ene, right? If I have but2ene and we have to react with ozone in presence of Zn and H2O. Okay, what product will form? Just remember one important thing. I'm going to share a very important trick. कुछ नहीं, यहाँ पे क्या करो? Just break the bond. Okay, along the double bond. एक हिस्सा बॉन्ड का एक मिल गया. This is one part and this is another part. तो दोनों एक एक पार्ट मिल गया. एक ओ को इधर वाले को दो, एक ओ को इसको दो और एक को जिंक को दे दो. तो मान लो एक ओ तुमने इसको दिया, तो this will become what? That is CH3 and CHO. सिमिलर वे में ए को आपने इसको दे दिया, तो ये भी क्या बन गया? CH3 CHO. और बाहर क्या निकल गया बेटा? बाहर निकल जाएगा हमारा ZNO है, तो H2 वगैरह निकल जाता है, उससे तुम्हें कोई मतलब नहीं है. तो बस ये ध्यान रखना है, ठीक है? बस इतना याद रखना है कि what product we get when we react but2ene with O3. So we get 2 mole of aldehyde. Similar, how will you get ketone beta? If I am taking CH3C, CH3, double bond, CH and CH3. And again, write the reaction with O3. What you will get? One oxygen is go to this part, that is, it will become CH3, C double bond O and CH3. So this will ketone, right? And one O is go this side. This is CH3 and CHO. So in this we get one ketone plus one aldehyde. Right? So this is the most easiest way to solve a question related to ozone lysis. So I hope you understood this and easily solve such question, right? But1ene give butane ozonide on ozone lysis. Just to remember this point, okay? Ki in which case you get propanol or propanone, or out of 2 moles of aldehyde plus 1 mole of ketone or 2 mole of ketone. Okay, so these are the questions. Basically, they are going to be come in ozone lysis of alkenes, right? Okay. Next point is reduction of ozonoid can also be made by zinc acid or H2 nickel or triphenyl phosphine to carbonyl compound. So this reagent is also used like zinc or acid or H2 nickel like that. I hope is it clear to everyone? This ozone lysis is clear? Okay. Now, next we move to alkynes. Okay, that is what is alkyne. And in alkynes, what we're going to study. Okay, so first of all, method of preparation, that is a calcium carbide on hydrolysis give acetylene. When we treat calcium carbide, or we say when the hydrolysis of calcium carbide takes place, then the formation of acetylene, or we say ethine is formed. Now, next is how will you prepare calcium carbide? Okay, let's discuss. Okay, when we treat calcium carbonate or we heat calcium carbonate, we all know the formation of CaO plus CO2 takes place. Now, this CaO, that is quicklime, combined with carbon to form calcium carbide. Okay, this is known as calcium carbide. Calcium carbide. This calcium carbide on hydrolysis produce calcium hydroxide plus acetylene, that is ethylene. Okay, so this is how you can prepare acetylene or ethine by using calcium carbide. Next, vicinal dihalide. We already discussed now what is vicinal dihalide, in which two halogen atoms are with the two adjacent carbon atom. So vicinal dihalides on double dehydrohalonation give alkynes. Base is used in this dehydrohalonation. कौन सा बेस यूज होता है? अल्कोहलिक KOH और सोडामाइड यानी NH2 ऑलरेडी डिस्कस हुआ. Dehydrohalonation reaction. So here this is a vicinal dihalide and we react with alcoholic KOH. Then the formation of what takes place? That is double bond. And again, when we treat this with same reagent, that is NaNH2, then the formation of ethylene or acetylene takes place. Okay, right. Next, terminal alkynes are acidic in nature due to the active hydrogen. This point is very, very, very important. If we considering out of terminal and non-terminal alkyne, which one is more acidic in nature? Always remember, beta, terminal alkyne are acidic in nature due to the active hydrogen. Now, for example, acetylene on reaction with the sodium forms sodium ethionate and dihydrogen. And this proves that because we know that what is acid, whenever the acid is treated with metal, what evolution of H2 gases takes place. Here also H2 gas is evolved. It proves that acetylene or the terminal acetylene having active hydrogen atom, and due to this they are very, very acidic in nature. Now, the next important point is acetylene on reaction with HBr form 1,1-dibromoethane. Okay, acetylene on reaction with HBr form 1,1-dibromoethane. For example, here this is the acetylene and reaction with HBr. Okay, so formation of what takes place, beta? Formation of bromoethane takes place. Okay, how? For example, I'm considering this is a negative and this is the positive. So negative part goes, okay, so this will become CH2, CH and Br. Again, HBr, that is CH3, CHBr2, that is 1,1-dibromoethane. Done. Next, propine on reaction with HBr form 2,2-dibromopropane. Similarly, if we treat propine, this is which type of alkyne? This is symmetrical or asymmetrical alkyne, beta? This is asymmetrical alkyne, right? So this is asymmetrical alkyne. So we use Marconi's addition here. Okay, that is the negative part. This is the negative part. This is the positive part. So negative part goes to those carbon atom which contain the lesser number. So this Br goes to this carbon. Okay, so wheel formation of 2,2-bromopropane takes place in case of asymmetrical alkyne. Similar, this one is also very important and came already in PYQ questions. Okay. Next, acetylene on a mercury catalyzed hydrogen give ethanol. Okay, acetylene on mercury catalyzed hydration give ethanol. This is very important. Okay, how? This is acetylene, and this is the hydrolysis in presence of mercury, that is HgSO4 on H plus. At 333 Kelvin, the formation of what takes place, that is CH2CHOH, and this form is very, very unstable. This form is very, very unstable, and tautomerism takes place, and this will convert it into ethanol because this is a stable form, right? Similar on when we treat propine on mercury catalyzed hydration, it gives propane. So what point is noted here? When we treat asymmetrical alkyne, it will give propanone, that is ketone, and we treat symmetrical, or we say acetylene, then it will give aldehyde, that is ethanol. So this point must be remembered, and this is very important topics in terms of questions, because many questions were asked from this topics only, right? Okay. Now, we cover already we cover alkene and alkyne. Okay. Now we are going to aromatic hydrocarbon, right? So this is very, very, 50% or more than 50% questions were directly coming from this benzene or aromatic hydrocarbons only. If I'm talking about hydrocarbon chapters only. Okay. So in hydrocarbon chapter, if three questions were coming now, then definitely one or two questions from this topic only, that is aromatic hydrocarbon only. So this topic is going to be very, 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 very important and very interesting as well. So let's start, okay, and try to understand what is the basic and what are the type of questions generally asked in this chapter for this particular topic, right? Okay. Now, first of all, Kekule is the one who proposed the structure of benzene, right? So Kekule proposed two different structure of benzene with the alternating double bond, as we see here, right? Okay. So Kekule proposed the two different structure. Kekule structure indicate the possibility of a two isomeric, that is 1,2 dibromobenzene. Okay, 1,2 dibromobenzene, right? Okay. Now, Kekule structure of benzene failed to explain unusual stability of benzene, and also failed to explain why benzene undergo substitution reaction rather than the addition, because it is a unsaturated having double bond, okay, multiple bonds. So why it will not undergo addition reaction, instead of it will go substitution reaction? So these type of question cannot be explained by Kekule. Okay, so these are the some limitation of Kekule. Now, if I'm talking about the benzene, the benzene contains 6 sigma bond, sp2 sp2 carbon, and 6 sigma sps, that is 6 hydrogen, and 3 pi, that is pp bond. Okay, so it having formula like C6H6. So having 6 carbon, and all these 6 carbon sp2 hybridized, okay, and 3 pi bonds, that is pp bonds. Now, what is the bond order of benzene? The bond order of benzene is 1.5. This is, remember, the ratio of the hybrid and anhybrid orbital in benzene is 3:2, and benzene acquire identical bond length, that is 139 picometer, irrespective whether this is a double bond, so it must be shorter, and this single bond must be bigger. But due to resonance, this double bond is delocalized. It is not permanently fixed to only one position. It will come around these. So we can better draw the structure of benzene as like this. Okay, this is called delocalization of, this is called delocalization of what? Electron. Okay. So benzene acquire identical bond length, that is 139 picometer, due to resonance, and benzene is a planar molecule with the dipole moment 0. This point also important. Benzene is a planar molecule, and we know that for the planar molecule, dipole moment is always 0. Right? Now, aromatic characteristics. So this is also very important thing. How will you determine the aromatic? Because many time questions were coming in your previous examination, and they were asked just identify whether it is aromatic compound or not, whether it is a more stable or not. So if we know the whether it is aromatic or non-aromatic, then we can easily explain the stability order also. Okay. So this is one of the important thing, how to determine whether the compound is aromatic or not. So let's see how we can judge whether the compound is aromatic or not by using Huckel rule. So Huckel says that molecules should be cycle. Okay, molecules क्या होना चाहिए? Cycle होना चाहिए. It must be planar. It must be planar. And delocalization of pi electrons is also present. If delocalization of pi electron takes place, then this is also the necessary condition for the molecules to be aromatic. And the one and last and most important one, that is the presence of 4n plus 2 pi electrons. That is Huckel rule. So if the molecule possesses these four characteristics, then it must be aromatic compound, right? So let's discuss with the benzene, whether benzene is aromatic compound or not. If I'm talking about benzene, it is cyclic, yes. It is planar, yes. Having sp2, planar means what? Having sp2 hybridization. Yes, 6 carbon having sp2 hybridization. And whether it will follow 4n plus 2 pi rule or not? Yes, it will follow 4n plus 2 pi rule. How? 4n plus 2 pi rule. It must comes out to be an integer, right? So if I'm talking about 4, how many double bond is there? That is 1, 2, and 3. That is 3. Okay. And plus 2. So how many? That is, yes. So how many number of electrons are there? There are 2 to 4 to 6. Okay. So 6 pi electrons are there. Okay. So this will be also follow. So presence of 4n plus 2 pi electrons is also there, right? So we can say that benzene is aromatic in nature. Similar, if I'm talking about naphthalene, naphthalene also having 2, and 2 means what? Having 2 cyclic ring, 2 ring, and total 10 pi electrons. This is 66 pi electrons, right? So, and this is also 6 pi electrons. So these all are the aromatic compound. So point to be remember here, if any molecule possesses this four characteristics, then it must be aromatic, right? Next, sodium salt of aromatic acid on heating in the presence of soda lime undergo decarboxylation to give benzene. So these two methods are the method of preparation of benzene. How will you prepare benzene? So whenever we treat sodium salt of aromatic acids on heating in presence of there is a soda lime, it will undergo decarboxylation to form benzene. Okay? Next, reduction of phenol. Phenol, when reduction with zinc, the removal of ZNO takes place and the formation of benzene also takes place. These are some very important and simple methods which must be remembered. Next, some some physical properties about the aromatic compound. Aromatic compound insoluble in water and burn with the sooty flame. Next, aromatic compound undergo electrophilic aromatic substitution reaction, and this one is a very important, because many questions were coming from this topic alone. That is, aromatic compound undergo electrophilic aromatic substitution reaction. Now, next, that is, benzene undergo nitration in presence of concentrated HNO3 and concentrated H2SO4. That is also known as nitrating mixture, and it will give nitrobenzene. This is benzene. This is concentrated HNO3, concentrated H2SO4, and we react with the presence of 323 to 333 Kelvin. Then the formation of nitrobenzene takes place. Sometime it may be asked, what is the role of concentrated H2SO4 in nitration? So you have to produce electrophile. To produce electrophile, right? To produce electrophile, we use H2SO4. Okay? Good. So this is the role of H2SO4 in nitration. Next, halogenation of benzene in presence of anhydride AlCl3, that is Lewis acid, give halobenzene. Okay, so this is the benzene react with the Cl2 in presence of AlCl3 to produce chlorobenzene. Similar, benzene on treatment with excess Cl2 in presence of AlCl3, it will give hexachlorobenzene. Okay, this is also known as BHC, that is benzene hexachloride. Benzene undergoes sulfonation when treated with fuming sulfuric acid and give benzene sulfonic acid like this. Okay, so this is when we treat with H2SO4, that is a fuming sulfuric acid. The formation of benzene sulfonic acid takes place, right? These all are the electrophilic aromatic substitution reaction. Now, the next reaction is benzene undergo Friedel-Crafts alkylation in presence of AlCl3 and give alkyl benzene. If I'm taking CH3Cl, then the formation of toluene takes place. If I'm taking C2H5, then the formation of ethyl benzene takes, right? So this is the Friedel-Crafts reaction. In this, which one act as the electrophile beta? In this, CH3 plus act as electrophile. In this, CH3, CH2 plus act as a electrophile. Now, benzene undergo Friedel-Crafts acylation in presence of anhydride AlCl3, that is Lewis acid, and give acetophenone. So this is known as Friedel-Crafts acylation. That is whenever the benzene is treated with CH3COCl, remover of HCl and COCl3, that is acetophenone takes place. Okay. Now, so these are the important electrophile that generally used in the reaction of benzene chain. For in chlorination, what is the electrophile? Cl plus. And what reagent you use? That is Cl2 and Fa. Nitration, NO2 plus is the electrophile, and what reagent we use? That is concentrated HNO3 and concentrated H2SO4. Similar in Friedel-Crafts alkylation, the reagent is R plus, and what reagent we use? That is RCl or anhydride AlCl3. Similar in acetylation, what is the electrophile? CH3CO plus, and what reagent we use? That is the RCl anhydride AlCl3. Same. Okay. So these are the electrophile and the name of the reagent we generally use in the electrophilic aromatic substitution reaction. Now, some important reaction of benzene, that is at a high temperature in presence of nickel catalyst, benzene show addition with H2 to form cyclohexane. Okay, so whenever the benzene is treated with hydrogen, it will form cyclohexane. Similar in presence of UV radiation. Okay, in presence of UV radiation, benzene show addition with Cl2 to give gamhexane, that is benzene hexachloride. It is also known as gamhexane. Just point to remember, gamhexane means benzene hexachloride. Combustion of benzene give CO2 and H2. We all know that whenever the combustion of hydrocarbon takes place, always CO2 and H2O is formed. Okay? Okay. Now, ortho para director direct the incoming new group at new ortho and para position. So this is the important thing. If the directors are ortho para directing group, whenever the electron donating group is attached to the benzene ring, whenever the electron donating group is attached to the benzene ring, it always increase the electron density and the ortho para position, and they direct the incoming new group into ortho and para position, right? Okay. Similar for the meta direction, meta direct the newly coming group into meta position. Whenever the electron withdrawing group are attached, then it decrease the electron density and the ortho para position. So incoming group is directed towards the meta position. So just remember some electron donating groups and electron withdrawing group. Electron donating group like OH, NH2, NHR, NCO, CH3, OCH3, and C2H5. So these are the example of electron donor group, which direct the incoming group to the ortho para position. Similar electron withdrawing group are NO2, CN, CHO, COR, COH, COR, SO3. These are the electron withdrawing group which supports meta directing reaction. Okay. Halogens are ortho para directing, but they are ring deactivating group. Just point to be remember beta. What are halogens? Halogens are ortho para director, but they are ring deactivating group because halogen is electron withdrawing group now. So they are deactivating group. However, due to presence of lone pair, they increase the electron density at ortho para position. That's why they are ortho para director, but they are ring deactivating group due to presence of chlorine. That is electron withdrawing group. Next, polynuclear hydrocarbon formed by the incomplete combustion of tobacco, coal, petroleum, and they damage DNA and cause cancer. So this point is also important. Polynuclear hydrocarbon, example polynuclear means more than one, that is a polynuclear hydrocarbon formed by the incomplete combustion, जो कि incomplete combustion से बनते हैं, of tobacco, coal, petroleum, and they damage DNA and cause cancer also, right? So these all are the important one shot uh, of hydrocarbon, right? Now we are going to solve some PYQ related to this topic we already covered today, okay? And try to understand what type of questions generally asked in the from this chapter, okay? Okay, the first question is the compound which will have the lowest rate towards the nucleophilic aromatic substitution treatment with the OH. We know that aromatic compounds generally go through, that is, if I'm talking about benzene, they generally go electrophilic substitution reaction. But in this question, they are asking nucleophilic aromatic substitution. So the compound which will have the lowest rate towards the nucleophilic substitution reaction. What is nucleophilic substitution? Nucleophilic substitution means someone wants to donate their electron, and benzene itself is a electron rich compound, right? So we कंसीडरिंग दोज ग्रुप, हम उसको पकड़ेंगे जिसमें क्या होगा, जिसमें कोई इलेक्ट्रॉन विड्रॉइंग ग्रुप लगे हो, जो इलेक्ट्रॉन को खींच रहे हो। जब ज्यादा अच्छे से खींचेंगे इलेक्ट्रॉन तो वहां न्यूक्लियोफाइल इजीली आके अपना डोनेट कर सकता है, बिकॉज न्यूक्लियोफाइल वांट्स टू डोनेट इलेक्ट्रॉन, एंड इफ इलेक्ट्रॉन डोनेटिंग ग्रुप आर प्रेजेंट, दे already increase electron density, and there is no scope for the nucleophile. In all these four options, if you're considering option number 4, that is whenever the electron withdrawing group is attached to meta, it always decreases this reactivity. So the electron withdrawing group are highly ineffective at the meta position in the nucleophilic aromatic substitution reaction. Hence, compound this will have the lowest rate nucleophilic aromatic substitution. Just point to be remember, beta, electron withdrawing group are highly ineffective at the meta position in a nucleophilic aromatic substitution reaction. So they have the lowest rate in the nucleophilic aromatic substitution, right? Okay. Now, the one giving maximum number of isomeric alkanes on dehydrohalogenation reaction is, we already study about the dehydrohalogenation reaction. What is dehydrohalogenation reaction, beta? For example, if I'm considering CH3, CH2, CH2, CH, Br, and CH3, we'll get 2-bromopentane. So what is dehydrohalogenation reaction? That is the reaction with KOH alcoholic. So in this, what is the formation? This is the alpha carbon, this is the beta carbon, this is also the beta carbon. So there will be the two products, right? One is CH3, CH2, CH, double bond, CH and CH3. Another is CH3, CH2, CH2, CH, double bond, CH2. Right? So which one is major? This one is major, we know from the dehydrogenation. But in this question, they are asking the one give maximum number of isomeric alkenes on dehydrogenation reaction. So if I'm considering the first one, that is 2 methyl, 1, 2, 3, 4, 2 methyl, 2 methyl bromo butane. Okay, we'll get only one. If I am considering this one, that is 2-bromopentane, we'll get two products, right? That is cis and trans. So the one which gives the maximum number of isomeric is 2-bromoprotein. This one, okay, that is two product. So this is also a very simple question based on the dehydrohalogenation only. Now the next question is, a hydrocarbon acts with the formula C6H8, uses 2 moles of H2 on catalytic hydrogenation, and a hydrocarbon having formula C6H8, right, uses 2 moles of H2. It uses 2 mole of H2 on catalytic hydrogenation of its own mole. On ozonolysis, X give 2 mole of methane dicarboaldehyde. What is the carbon X? What is the hydrocarbon X? Batao. Can anyone guess? Yeah. Okay. So this is the cyclohexane. This is C6H8 because here C6H8 on 2H2 reaction with 2H2. Okay. So on ozonolysis it will give 2 mole of this. 2 moles of what? That is the 2 moles of dicarboaldehyde. So cyclohexa 1,4-diene, that is option number 4. Cyclohexa 1,4-diene. This is the structure of cyclohexa 1,4-diene. So this is the correct answer, right? Next. Halogenation of which one of the following will give the meta-substituted product with respect to the methyl group as a major product? Okay. So halogenation of which one of the following will give the meta-substituted product with respect to the methyl group as a major product? Okay. So meta-substituted product, right? So we know that whenever NO2 or CHO, they both are what? They both are electron withdrawing group. Okay. So we have to find meta substituted product with respect to the methyl group as a major product. Now, electrophile will attack at orthopara position with respect to the better electron releasing group, that is electron donating or electron releasing. If I'm considering OH and CS3, OH is a better electron withdrawing group. Now, para position with respect to OH, that is R group, and it will meta position with respect to CS3 group. So what will be the correct answer, beta? Yes, that is CH3 and CH3 and OH, right? So this will be the right answer. How we can say that CH3 and OH? Because if I'm talking about electron donating group or electron releasing group, then OH having more tendency than CH3 and para position with respect to the OH plus R group, and it will be most meta position with respect to the CH3 group. So we can say that CH3OH will be the correct answer for this question. Now, product A of the following sequence of reaction is given ethyl benzene. Now, whenever the ethyl benzene is treated with Br2Fe, Cl2, alcoholic KOH, what will form? A, B, C, D. So, try to solve this question. What the product you will get, beta? When we treat ethyl benzene. Let's discuss. Whenever we treat ethyl benzene with Br2Fe, the formation of bromoethylene benzene takes place. And when we treat this with Cl and heat, then this is called benzylic halogenation. Then the formation of CHCl, CH3 takes place. And next, that is the elimination reaction with alcoholic KOH. The formation of this takes place. That is CH double bond CH2 and Br. So which one is the correct? Which one is the correct? That is option number D. Option number D is absolutely correct, right? Next, which of the following is the Lindlar catalyst? Zinc chloride in HCl, cold dilute KMnO4, sodium and liquid ammonia? No, no, no. That is partially deactivated palletized charcoal. So this is the Lindlar catalyst, right? The next question, in a Friedel-Crafts alkylation of aniline, one gets alkylated product with the ortho and para substitution, secondary amine after acidic treatment, an amide product, or positively charged nitrogen and benzene ring. So beta, this is aniline, right? This is aniline. When we treat aniline with CH3Cl in presence of anhydride AlCl3, then the formation of what takes place? That is NH2 and AlCl3. Because N having lone pair of electron, through this, it will accept this AlCl3, and the formation of positively charged nitrogen at the benzene ring takes place because their lone pair are uh, consumed in making bond with AlCl3, right? So formation of positively nitrogen on the benzene ring takes place. So we'll discuss questions, okay? So we'll discuss many PYQ questions related to this chapter, right? And we also cover entire chapter in one shot, that is alkane, alkene, alkyne, and hydrocarbon. Try to read this, try to solve as many questions as you can. Okay, try to solve the PYQ question just considering these points where whatever point we discussed today. Try to learn and utilize this point in solving your question. So if you have just practiced 1 to 2 times now, then you will be able to solve such questions, and it's not very difficult. Okay, so just try to learn this, whatever I told you in today class, and then you will be able to solve questions related to this topic. Okay, so let's, yeah, if you have any doubt, beta, anyone having any doubt, you can ask. Okay, so let's summarize this class. So today we're basically हाइड्रोकार्बन से रिलेटेड सारी बातें करी, एल्केन्स, एल्काइंस, एल्काइंस सबको कवर किया हम लोगों ने अच्छे से. ओके। एंड पीवाई की क्वेश्चन भी कुछ कंसीडर किए, तो अब नेक्स्ट क्लास में मिलते हैं और वहां हम लोग देखेंगे अपना जो नेक्स्ट चैप्टर है, दैट इज chemistry in everyday life and environmental chemistry. So we are going to solve this question. So these are the very very important topic. So आज ये करो इसको अच्छे से, और नेक्स्ट क्लास में मिलते हैं, फिर वहां पे स्टार्ट करेंगे। टिल ऑल द बेस्ट, टेक केयर, और अच्छे से पढ़ते रहो। ओके।